So 6.2 deals with volumes. So in trying to find the volume of a solid, we face the same type of problem as in finding areas. We have an intuitive idea of what the volume means, but we must look at this idea in more precise calculus definition. So here's a nice simple shape that we might be used to, right? Just a simple cylinder. To find the volume of this cylinder, like many other shapes, what we want to do is convert it into sort of a two-step process. First, we want to find the base. Let's see if I can highlight the base for this thing. So in red, the base is sort of the ground of this thing over here. It's this down here. So if we can find the area of the base, find that area and then multiply it by its height, the area of the base times its height would give us the volume. So if we can find the equation, or if we can get a nice equation for that area, that basement, that base, then it should be easy to find the volume of the whole thing. So in general, the general guideline we want to see, we want to use is that we want to convert volume into a multiplication of an area times a height. Okay, so this is in particular, a right cylinder. So area B sub 1, called the base, and congruent region B sub 2 is parallel to the plane. Okay, so we got the cylinder consists of points on line segments that are perpendicular to the base and joint B1 and B2. The area of the base is A, and the height of the cylinder's distance from B1 to B2 is H, and the volume is area times the height. Okay, so as we suspected, so B2 is the roof of this thing, so it's this guy up here. And then the height is the distance between the two, right? Very often we work with, say, just a simple cylinder. If this was just a simple cylinder, it would be the area of a circle up at the top end, and then we'd have this area of a circle down in the bottom end, and then we'd connect the two, and the distance between the two would be the height. And so we get just a nice simple can. Like this. So this is kind of connecting this way, and we'd have a straightforward cylinder. Good. So if it was a straightforward cylinder, then the area would just be a constant value, since it would be consistent throughout the whole thing. So this might be just some constant area, capital A, would be that guy. If we were given, say, the value of the radius, remember that the area of a circle is pi r squared, so we would end up with pi r squared, and then we toss in that h for the height, and we get the volume is equal to the height times pi times r squared. Pi is a constant, so it seems kind of silly to stick a constant in the center. So pi h r squared if it was a straightforward cylinder. Good. Good. Okay, but we're going to be looking at cases where it's not necessarily a straightforward cylinder. So just the general formula that we're going to be working with is that we want an equation of the area times its height, where that equation might vary. It might not be a constant value. So here is a standard cylinder, radius r. The base is then going to be equal to pi r squared h. Well, the base is pi r squared, and then times h would give us the volume. Or we might be looking at a rectangular box like this. So again, we can think of it as the base, which would be this rectangle down here, the floor of it. And then we got to multiply it times its height to get the volume of the whole thing. So the rectangle is length times width, and then we just multiply that times height, and that'll give us the volume of the whole thing. Good. So in each of these cases, we think about the volume by thinking of it as an area multiplied by a height. And that's fine as long as we have really simple shapes, but of course they're going to get a little bit more complicated. So for a solid S that isn't a cylinder, we're simply going to adopt the idea of kind of cutting it into little pieces, and then approximate each piece as a cylinder. So we're going to approximate it to be little cylinders, which are often referred to as coins, the coin method. And we'll see what that looks in a second. So we estimate the volume of S by adding the volumes of the cylinders. We arrive at exact volume of S through a limiting process in which the number of pieces becomes large. Okay, so this is we start by intersecting S with a plane and obtaining a plane region that is called the cross section of S. So here's an example. A nice pretty graph here. So we have this sort of a shape here that looks like a loaf of bread or something, right? So this is a 3D image, and we want to find the volume of that image. So what we're going to do is we're going to take this plane and go right through it. It's almost like we cut it, cut right through it. And we're gonna have something like a slice of bread, right? A slice that comes out of this. We're going to approximate the area of that one, and then we're going to do the rest. We're going to chop it up into, say, maybe 10 different slices, find the area of each one of those slices, add them together, and that'll be an approximation to the whole thing, but not a very good one with just 10 slices. So it might look like this. 1, 2, 3, 4, 5, 6, 7. Here it is with 7 slices. So we would find the area of each one of these 7 slices. Each one of these 7 slices, we add them together, and then that gives me a pretty good approximation of this. And of course, if you want a better approximation, don't make it 7 slices, make it 10 slices. That's a better approximation. Make it 20 slices, make it 100 slices, right? So we can always increase the number of slices, and we'll get an even better approximation. And if we can rewrite it so that we can do a limiting process, let the number of slices go up to infinity, and if that limit exists, then we can find the exact answer. Okay? Good. Questions, 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 questions? Okay. So here we have let A of A be the area of the cross-section S. So that would be this purple thing is A of X. So it's an area of this purple thing written as a function of X along the X-axis. Good. So think of a knife cutting through a slice. Okay, so when we do that, each one of these slices is going to have a little width. Right? Now the actual original one, it's got this kind of a smoothness happening here. And notice that when we approximate it, we kind of get rid of that smoothness and just use more of a flat shape. Also, notice that there's a little gap that occurs between one slice and the other because of this approximation. Good. So that's why there's going to be, it's one of the reasons why there's going to be an approximation when we use these slices and not going to get the exact value unless we apply a limiting process to this and let n go to infinity and that limit exists. Good. So let's zoom into this guy a little bit. So we slice through it at x, and then we're going to have x sub I minus 1 and x sub I, and then we're going to have an x sub I star. So this is referring to us breaking up our entire segment of the domain that we're interested into n equal slices, right? So the ith one is going to be the one that ranges from right? So the ith slice ranges from x sub I on the top end, the upper end, and the lower end would be x sub I minus 1. Good. So this is the little segment that goes through there. And now somewhere in there, we're going to pick a value of x sub I star. And x sub I star is going to be a value which is being used to find the area of in here. Good. So then we multiply times the difference between these, and this would be kind of like the h, right? The height. If we take this slice of bread and we lay it down on the floor, we can think of it as we can think of this slice by finding s, the area of the purple, times delta x, which is the same thing as the h. Does that make sense? Sort of, kind of, maybe? Sort of, kind of, maybe? Okay, so for each one of these 7 slices, we're going to have 7 different volumes. So this volume here, the first volume, is going to be based on some x sub star 1. Right, there's going to be some volume sub star 1. Come on, 1. Good. So in the space between x sub 0 and x sub 1, somewhere in here, we're going to kind of pick a value of x sub 1 star, and then we're going to use that value to find that volume of that first slice. Good. That volume is going to be equal to the delta x, which is the difference between these two values. Right? Well, I shouldn't have done that. The difference between these two values is delta x. The difference between any of these two values is delta x. Right? So the volume is really going to be equal to the area. That's a function of x sub star 1 times delta x. And that'll give me the volume of that first slice. The second slice is going to be the same thing. It's going to be some area of x sub 2 star, where x sub 2 star is some value in between x sub 1 and x sub 2. Right? Somewhere along, say around there, about there, x sub 2 star exists. And then we're going to find the area, multiply that times delta x, and then together that gives me b of x sub 2 star. Right? Dot, 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 all the way out to the last one. In this case, there are 7 of them. So this is going to be a of x sub 7 star times delta x, which is volume of x sub 7 star. Good. So we're going to say that approximately, if we add up all those volumes, we get an approximation to the actual volume we're interested in. Right? The volume, the real volume. We're going to say it's approximately equal to v of x sub 1 star plus v of x sub 2 star plus dot, 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 and I know that goes out to 7. That should be v plus v of x sub 7 star. There's 7 slices that we did. Okay? Well, a better way to write that would be to say that this is the sum as I goes from 1 to 7 of volume of x sub I star. And that's approximately this volume. Right, where the little counter goes from 1 to 7, and then that's where I turn this little I here into a little counter that goes from 1, 2, 3, dot, 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 all the way out to 7. Good. And just like before, the volumes are actually equal to these things. So another way to say it, instead of saying the volume, is to say that it's equal to the sum as I goes from 1 to 7 of the area of x sub I star times delta x, where this x star sub I is being guided by this little counter here, but this delta x is just a constant, right? It's just some constant that represents the widths of each of these. Good, 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 good. Okay, and so I think that that's pretty much where we're at here. So each individual volume of each individual slice, V of S sub I, the ith slice, is equal to the area times the height of that individual slice. And so we can write it this way. So here I did just for the 7 slices, but if I was doing n slices, it would go from I goes from 1 to n instead of 1 to 7. Right? So here, this is just for this particular case where there are 7 slices. But if we have n slices, then we would just change this to n, and that's where this little formula comes from. The volume is approximately, right? These little squiggly equal signs indicate that it's an approximation. So the volume is approximately the sum of these areas times these widths, right? Times delta x. Good. Good, good. And then, of course, what we're going to do is let n go to infinity, and we see that that's a better and better approximation to the volume that we're interested in. Good. So in this loaf of bread picture, if we let n go out to infinity, the more slices we have, the better and better the approximation gets. If we let n go out to infinity, and that limit exists, then we'll be able to find the exact volume of that shape, that object. Good. So we let the limit, as n goes to infinity, of the sum from 1 to n of, and then we have this little product. It's going to be the area as a function of x sub I star times delta x. And if you recall from our definitions of integrals, this is exactly the definition of this integral. It's the integral from a to b of a of x dx. Good? Sort of, kind of, maybe. Okay. When we use volume formulas, the volume is equal to the integral from a to b of f of x dx. It is important to remember that a of x is the area of a moving cross-section obtained by slicing through x perpendicular to the x-axis. So that's because we have a dx here. We might have something that's perpendicular to the y-axis if we have a dy. So we'll go through examples in a little bit. Notice that for a cylinder, the cross-sectional area is a constant. Right? A of x is equal to just some area A for x. So our definition of volume gives that v equals to the integral of from a to b of a dx, where a is a constant we factor out. Therefore, the antiderivative is just going to be x, which then gives us a equals to b minus a. Good. Here, I don't know if this is. So this is, for example, describing a cylinder on its side. I think maybe this needs a little bit more assistance here. And this is where we get to my first big problem in this section. I can't draw. So kind of a cylinder on its side, like this. And here is the y-axis, here's the x-axis. And so we have this, and so this guy goes from A to there, from A to B. So here's this cylinder floating above the x-axis, And of course it's a 3D cylinder, so I have to have, there is technically a y-axis that pops out toward us, but we're ignoring that for a second. So it's just floating above there. So now if we take a little slice and we cut through the cylinder like this and kind of get a little width to it, so it ends up looking like a coin. This first section, this first technique is often called the coin technique. Oh, that's really ugly. You get the point. Okay, anyway, so it's like a little coin, and this is like the side of the coin. And here's the center of the coin. Little coin method. Okay. All right. So we're gonna find a little value there. So this would be the x sub I star. The width of this coin is going to be the delta x. Right? It's the width across it. It's a delta x, and we're just going to find the area of the face of this coin. So if we can just find the area of this circle in here. Right, just the area of this blue one. Well, the area of a circle, area of circle is pi r squared, right? So, but in a nice cylinder, a simple cylinder, the radius is always going to stay the same, right? I don't know what it is, but let's say, just for the sake of this drawing, let's say it's 3 units. So that means that for this purpose, we're always going to have a 9 pi, right? So in this thing, since the radius is 3 units, then this is going to be area of 9 pi. Good, good, good. No matter where I slice this, the face is always going to be a circle that has a fixed area. Good. And now the height is going to be this distance here. So based on my picture, I could see that the volume should be equal to the 9 pi, which is the area of the circle, times the height. Good, 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 good. Okay, but now following this description here of the integrals, okay, so I'm going to get a coin, and that coin is going to have a certain area, and it, for this blue part here. So it's going to be some area that's a function of x sub I star, and then we're going to multiply that times its width, which is this dx. Good. And then we want to add up all of those. So this would end up being the volume of the of this particular coin. Volume as a function of x sub I star is equal to this. And so my approximate volume for the whole thing is going to be equal to 2 parts. One, I want to come up with a Riemann. Goes from 1 to n of this a of x sub I star delta x. And then I also want to have the limit as n goes to infinity of all of this. Good. Okay, so then my volume is going to be the integral starting from a to b of a of this x sub I star dx. Now, for a cylinder, as we've already pointed out, this is just some constant. So this is going to end up equaling the integral from a to b of a constant. Now, if I said the radius was 3, then that area is just pi 9 pi dx, or just some constant, which we can factor out, which we end up with 9 pi integral dx from a to b. The antiderivative, right, we can think of putting a 1 there, would just be x ranging like this. And so this is 9 pi times b minus a, right, which is exactly what we intuitively thought it was based on the picture. Any questions? So that's where this comes from. A is a constant, we can factor it out, and then what we're left with is the integral of 1 dx, and that's where we end up with the b minus a. Kind of, maybe, sort of. Any questions? No? Okay, so let's take a look at example number 1. Show that the volume of a sphere of radius r is v equals to 4/3 pi r cubed. Okay, so that might look like a familiar formula you were forced to memorize at some point. So here we're going to actually derive it. Okay, so there's this nice little image here of a sphere, a ball, centered at the origin. And we're going to apply this procedure of taking a slice and creating coins out of it. Okay, so we're going to think of this guy here, and we're going to come through with our knife and cut right through this guy here, and then we'll end up getting this guy right here, except we have to consider that it's going to have a thickness of some kind. Okay, so we're going to have a little thickness. I'm exaggerating it so that we can see it, but in reality it's going to be a very thin little guy, but it's going to have a thickness to it. Okay, so that thickness is going to be this guy right here. And it depends on where we slice it, the direction in which we slice it. The way I've sliced it right now, it is perpendicular to the x-axis. So therefore, this little thickness guy here, the thickness of this is going to be a delta x. Good. Okay, so let's use technology to improve upon that a little bit more. So I'm just going to do something and not going to explain it too much right now because I think just want to get to the graph and I don't want to bog you down with all that detail. So let me just jump to this. I'm going to do the equation of a circle. Now this program does not let me do the radius r. I have to lock something down. So I'm just going to do it for 1 and then hopefully just to get the image, and then from that hopefully you can visualize where the r comes in. So let's say that it's got a radius 1, a ball of radius 1. That's of course dominated by x squared plus y squared. So let's do this, x to the second power. To the second power to the 0.5. Let's copy that. Okay, that takes me to that circle. And then -1 times b. Whoa, that is not. I thought I copied it already. What in the world is all that? Real? Okay, there we go. Perfect. Okay, so what I did was I thought of a circle, right? So going back to a standard two-dimensional grid, where we have our y-axis there and x-axis there, then of course we know that if we have a circle, wow, that's really ugly, but that's supposed to be a circle. Let's do that again. Well, not much better, but anyway, a circle. A circle is described by x squared plus y squared equals to r squared, centered at the origin, right? Centered at the origin. And so if we just take a standard one, that's just going to be a 1, x squared plus y squared equals to 1. Then I can solve for y equals to plus or minus square root of 1 minus x squared. So then the plus, right, the plus gives me the top half of my circle. So this guy there is y equals to root 1 minus x squared. And then the bottom half of my circle, that guy, that's going to be y equals to minus root 1 minus x squared. Okay, all right, so that's what I typed into the system. And then of course remember that instead of a giant root, I could say that this is the same thing as 1 minus x squared to the power of 1/2, or 1 minus x squared to the power of 0.5. And this one is negative 1 minus x squared to the power of 0.5, or negative 1 times. Okay, so that's what I typed into that program. And what that does is that it creates the circle in the plane, the xy plane, and then the system will generate a sphere out of that. Okay, so that's what I did for this guy. Okay, and so now we have a nice little sphere. Of course, like I said, this program limits me because it doesn't let me type in a variable for the radius of r, so we just have a 1. So this is a sphere with radius 1, but we can get the image we want out of it and be able to use it for the purposes we need. Okay, so we have this little sphere like this, right? The blue sphere. And what's going to happen is that as we slice it, right, we can choose to slice it in this direction, perpendicular to the x-axis. And if we do that, we're going to get this yellow coin thing. Now, the actual size of the yellow coin will depend on where I slice it, right? Because if I slice it closer to the edge, see how that yellow coin gets smaller, right? Because it's closer to the edge. And if I slice it closer toward the center of the sphere, I get a bigger coin, right? The biggest coin will happen right there, right at the center. Right at the center, we'll get the biggest coin possible out of this thing. Good. Okay, so what we want to do in this coin method is that we want to come up with an equation for one coin, right? We're going to take the x-axis from negative r to positive r. We're going to chop it up into n equal portions, and those will be the thicknesses of our coins. And for each one of those individual coins that's generated, we want to find its area, its volume. Okay, so now let's take, can't do that. Okay, so we want to take one individual coin. So I'm just going to take a picture of this guy. Let's see if I can zoom in just a little bit more. That's good enough. Okay, so let's say that I want to take a picture of this and I can write all over it. All right, let's go over here. Okay, so we are going to be dealing with a situation where the radius of the sphere is lowercase r, right? So that means that if I go out from the origin out to this point right there, along the axes, I think that this ends up being negative. I think this is like the x-axis, I believe. And this, let's say that that's the y-axis. Oh, y-axis over there, so that's called the z-axis over there. Okay, so then this value for us right here will be negative r, right? Because the radius from the center of the origin up to there is r, and the distance from there to there, out to that point out there, will be positive r. Also, the distance from there all the way up to the very, very top of the sphere is also going to be r. And so will it be down here, right? Because it's an r. So everywhere there is a distance from the origin to a place along the surface of the sphere is going to be a distance of r. So along the number line, it might stretch out down to negative r, right? Because it's a distance, an absolute value distance of r, everywhere we go. Okay, so now if we slice it perpendicular to the x-axis, oh, and that looks a little weird. If we slice it perpendicular to the x-axis, we're going to have a little thickness, the little thickness of this coin is delta x. And now to find the volume of that coin, we need to figure out the radius of the yellow one. So if I want to figure out the height from, well, let's put it in red, I guess. If I want to figure out the height from there coming down to there, right there, this distance from there to there, that distance, I'm going to call that, I don't want to use lowercase r because that's the radius of my sphere. Let's call it capital R. It's still a radius, so r, but capital R. So don't confuse that with lowercase r. Lowercase r for us is going to be some fixed value, right? They're going to tell us what r is, but for us, lowercase r is a fixed value, whereas capital R is going to vary depending on where we slice it. As we pointed out before, that if we slice it close to the edge, we're going to have a very small yellow circle. And if we slice it toward the center, we get an even bigger yellow circle. So the value of capital R is going to vary. Okay, so now what we want to do is think about the triangle that connects the origin to the top of that coin. And let's see if I can make it thicker maybe. If I connect them, I end up with something like this. And so I end up with a right triangle. Oh, come on. A right triangle there, like that. And so the distance from the origin to that point right there, that's going to be some value x. I'm going to leave that there because it's on the x-axis. And I know we use x way too much, but it's a value x on the x-axis. And then in this direction, this ends up being lowercase r, right? Any distance from an origin to a surface on the sphere is always going to be lowercase r. Good. Okay, and so that is governed by Pythagorean theorem. So lowercase x squared. So lowercase x squared plus capital R squared is going to be equal to lowercase r squared. Good. So if we solve for capital R squared is going to be equal to r squared minus x squared. And so r is going to be equal to plus or minus the square root of r squared minus x squared. And from my picture, I can tell that I'm not interested in the negatives, right? I'm only interested in the positive value of r. So capital R is just equal to r squared minus x squared, right? Capital R is the radius of this yellow circle, so we're not interested in considering negative r's at this point. Okay, so now that we have an equation for capital R that will depend on the value of x, right? As x ranges left and right, as we slice this up and down, depending on where we slice it to get our different coins, we'll get an equation that gives us the actual value of capital R. And once we have capital R, well, now we have this other image. Let's go back to over here. Okay, so now if we want to look at at the yellow coin, we can twist it around, right? We can twist it around so it's just facing right at us. And we know that as we slice this, again, it's going to be either really big or much smaller, 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 depending on where we're slicing it, right? It gets small or it gets big. So if we want to find the area of this yellow circle, this kind, let's go back to here and okay. So now twisting it around, here's that same yellow circle. And now we know that the height from there to, well, let's make it thicker. From there to there is going to be capital R. And it varies, right? Lowercase r is a constant. Capital R is going to vary depending on where exactly we slice it. Okay, but if we have this, then we know that the area of this circle created, well, the formula for the area of a circle, area of circle, is always equal to pi radius squared. Right? It's pi r squared, where r is the radius, but I didn't want it to confuse it with other things. So area of a circle is pi times radius squared. So for us, the area of this yellow circle, so the area of this circle, this particular yellow circle, is going to be equal to pi capital R squared. Okay, capital R squared. And well, okay, actually, if we go back over here, capital R squared was just equal to r squared minus x squared. So it's going to be equal to pi times lowercase r squared minus x squared. Right? Remember that lowercase is a constant. It's the radius of the original sphere. That doesn't change for a particular ball. But the capital R will change. It changes, it varies. And it will vary based on x. It'll vary based on where we make our cut, our slice. Good, 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 good. Okay, so this is area. This is a two-dimensional thing. It's the area of this yellow circle. But we're really interested in the volume of my coin. The volume of my coin will be equal to the area, the surface area of that coin, times its thickness, right? So now I can just say, back to this guy now, like this three-dimensional thing, the volume of one yellow coin will be equal to the pi times the r squared minus the x squared, depending on where the x is, right, where I cut it, times the delta x. Good. So that'll be the volume of one yellow coin. Good. Okay, so then if we wanted to do a pretty good approximation of the volume of this sphere, what we want to do is chop up this whole thing into n equal coins. So I'll say an approximation, for the volume of the sphere will come if we do n equal slices. So it's going to be approximately equal to the sum as I goes from 1 to n of n of these coins, where we'll have pi r squared minus, and then x sub I star squared times delta x. Now, what is this x sub I squared deal about? This is a particular value within our segment, right? So what we're going to do is we're going to take this entire segment line for the x-axis, and we're going to chop it up into n equal portions. And so let's take this. It's really messy, so I don't want to write inside there. So let me just take that number line and pretend it just comes out this way like that, and it goes from negative r all the way up to r, right? And there's this whole sphere right above that, right? So I just kind of stripped away everything except for the x-axis. Okay, so we're going to take that space and we're going to chop it up into n equal spaces. Good. So each one of these spaces is going to be a delta x, right? So we're going to have each one of these is going to make up a coin. Good. And then inside each one of these spaces, we're going to choose a randomly selected value inside there. It doesn't, well, as we learned earlier, it doesn't have to be a randomly selected value, but for any choice of x sub I such that x sub 1 star comes from the first coin, and then x sub 2 star is going to be somewhere in the second one. Not necessarily right in the middle, but anywhere in there. X sub 3 star is going to go somewhere in there as well. So as we go dot somewhere in the ith one, this is the ith space. It'll still have a width of delta x, so it'll still have that same width of delta x, but somewhere inside there we'll be able to pull out the ith one, x sub I star. Good. All the way out to the last one. So the last one on here, as before we get to that r, will be some nth value, x sub n star. Good. Once we make a choice for each one of these can be plugged into this formula to come up with each of the coins that will come together to give me a good approximation for this sphere. Good. All right, so that's where I got this from. And so this makes an excellent approximation as long as n is sufficiently large. The bigger it is, the better my approximation. Good. And then, of course, if we don't want an approximation, we want the exact answer. We want the full volume. Well, then not an approximation, but the actual volume will be equal to this. The actual volume of the sphere. Come on. Shit. Okay, the actual volume of the sphere is going to be equal to the limit as n goes to infinity of this exact same thing here. It's going to be the Riemann sum as I goes from 1 to n of pi r squared minus x sub I star squared dx. Good. Okay, and that looks an awful lot like our definition for an integral, right? So then we'd say the volume of the sphere is equal to the integral of, and then we have pi r squared minus x squared dx, and this is where x ranges from negative r to positive r. Okay. Looking at our picture, should be guided by that. You see that we're going to apply this process as x ranges from this. The farthest left value is negative r, and we're going to apply it all the way out through positive r. Right, we're going to break up that segment into n equal spaces, like we did here. X ranges from negative r to positive r, but then we're going to let n go out to infinity. So there's an infinite number of tiny little things, an infinite number. So then eventually the thickness of each coin is going to become infinitely thin, almost like a little piece of paper, smaller, thinner than a piece of paper, infinitely, infinitely thin. And we're going to find the volume of each of those coins. We're going to add them all together, and that will give us the volume of the entire sphere. Okay, so that's what we're tasked with figuring out now. That's the integral. That's the hard part, setting up that integral. Once we have that integral set up, then all we have to do is find it, and that'll be our answer. Okay, I'm going to copy it over. That's fine, I'll just do it right here. Okay, one shortcut we could do is by symmetry note that if we just find half the sphere, we can double it, and then that'll give us the whole sphere. Okay, so we can say that the volume of my sphere is equal to the integral as x ranges from 0 to r of pi r squared minus x squared dx, and that's just going to give me half my sphere, right? I'm going from 0. If I just start off at x goes from 0 to r, instead of from negative r to positive r, just from 0 to r, I'm going to get half my sphere. So if I want the full sphere, all I have to do is multiply that by 2. It's just symmetry. And one of the reasons why we like doing that is because whenever you can introduce a limit of integration that involves a 0 or a 1, usually good things happen. Okay, so now let's just go ahead and simplify this. My volume, my volume of the sphere is going to be equal to, I'm going to pull out that pi, that's just a constant, 2 pi, parentheses, and now r squared, remember r is a constant, so, and the variable of integration is x, so we'll end up with xr squared minus, and then here, using our antiderivatives, polynomials, I know it's going to be 1/3 x to the third power, right? Kind of guessing and checking. Now I know that if I take the derivative of this, bring down the 3, cancels with the 1/3, subtract 1 from the exponent, we get to that guy. Evaluated as x ranges from 0 through x goes up to lowercase r. Good. Almost there. My volume of sphere then is going to be equal to 2 pi times, and it's going to be something times r squared minus 1/3 times something to the third power minus something times r squared minus 1/3 times something to the third power, like that. And so we apply r, so that's going to go there, r, and then we apply 0. That's going to be minus 0 and 0. Okay, luckily, as we had foreshadowed, anytime you can throw in a limit of integration with a 0, good things happen. 0 times anything is 0. 0 times anything is 0. 0 minus 0 is 0. So this whole thing is just 0. And so it just simplifies to this right here. And that is just going to be equal to 2 pi times r cubed. R times r squared is r cubed. Minus 1/3 r cubed. Right, let's put a common denominator here. This could be 3 over 3. So that's going to be 3 minus 1. That's just going to be 2/3 r cubed. And so my volume of sphere becomes 2 pi times 2/3 r squared, r cubed. And then 2 times 2 becomes 4. So we get that our volume of our sphere is equal to 4 pi r cubed over 3, 4/3 pi r cubed, right? Which is the formula that we were trying to verify. So we got to our answer. Confirm that that really is the formula we memorized so long ago. Let's double check that that's what we get over here. Oh, okay, yeah. So the setup is the hardest part. Figuring out, how do you organize this in a way that you can present it. So steps are going to be to get a good sense of the image you have, and you're welcome to use technology, that GeoGebra site that I'm using, or Desmos, or whatever else you have. Get a good sense. After you do a couple of these, you can kind of visualize them, even if you're not a very good artist. I'm a terrible drawer, so I could never do this beautiful little sphere thing on my own. But at least you kind of get a sense of what it is, and maybe you won't need it as much. But anyway, get a good sense of the three-dimensional image that we're dealing with. In this particular technique, we're doing the coin method, so you got to think of a way to cut it, and now you might be cutting it perpendicular to the x-axis, or we might go in the other direction like this and slice it perpendicular to the y-axis or the z-axis, right? So it depends on the image. Sometimes one direction will be more advantageous than the other. Sometimes it doesn't matter. In this case, with a sphere, it really wouldn't matter which direction you decide to chop things in. You just have to be careful about it and consistent about your work, but you can do it in any direction. But as we'll see, in some figures, one direction makes sense, in another direction it might not make sense. Okay, so get a good sense of what it looks like, chop it up, decide how to chop it, perpendicular to the x-axis, to the y-axis. You're going to create some coins. Think about how to find the radius of each coin, and remember that as you slice it in different places, the radius is going to vary. So we want to be able to marry or find a function of the radius as a function of the x value, so that you plug in an x value and you tell me the radius. Plug in the x value, tell me the radius, right? So we want the radius equals to some equation involving the x-axis, if you're doing it perpendicular to the x-axis. Or if you're going to do it perpendicular to the y-axis, then we want the opposite. We want an equation where the radius of the coin is equal to some function of y, if you're going to do it that way. Okay, so come up with some equation. that involves the radius of the coins. Then we want to use our formula for the area of a circle, and then tie that into the volume of a coin to find the volume of each individual coin. And then you can take that to this thing, right? You don't have to do these two steps moving forward. I was just trying to point out where it comes from. But very often people skip that step and go to this. So you kind of visualize with what one coin is. Be careful about your variable of integration. Make sure that they match. We got the variable x there, dx, right? This is analogous to the delta x, the dx. Good. And then this is the this is going to be the volume of one coin, sort of inspired by what the volume of one coin is. Good. And then just integrate that. Now keep in mind that there might be some nice shortcuts we can take advantage of. Sometimes we can just focus on quadrant 1 and notice some symmetry. It might be easier to deal with quadrant 1 where everything is positive and pretty, and then just quadruple it or something like that. So be careful with or always be aware of possible shortcuts that make the integral easier to deal with, particularly if you can insert a 0 in there, because as you can see, it's really nice to work with x equals to 0 when we're trying to evaluate this. Good. Okay, so let's move on. Let's see what the author did. Very, very similar, I hope. Okay, so the same nice spherical image, and we slice it this way, giving us a little coin there. A cross-sectional area of the coin is going to be equal to pi y squared. Okay, so that's another, instead of capital R, the author called this y. Okay, and we saw that y is equal to, or it's governed by the Pythagorean. Right, so the distance from here to there is x, and then we have lowercase r, which is the radius of the sphere, and then we have the distance y, which is going to be the radius of the little coin. Right, this is a little coin that kind of comes this way. It's got a little thickness to it. Maybe it's a little too. It's got a little thickness to our coin. And then that thickness is that delta x. Good. Okay, so the area of the purple coin for them, I was doing yellow coins, so purple coin here, is going to be equal to pi radius squared. And then the author used y as the radius, so that's going to be pi y squared. Good. But also we know that x squared plus y squared equals to r squared, Pythagorean, just like we did before. So if we solve for y squared, we get r squared minus x squared, which is where we use this formula, plug that in, and we get pi times r squared minus x squared. Right? That's what this is. So this is the area, the area of the coin once you chop it up. And then all we have to do is multiply this by the thickness, which is delta x, to get the volume of one coin. So from that, we can set up our integral. The integral ranges as x goes from negative r to positive r of the area of the coin times its thickness to give us our volume. Good. So we can plug that into here. That's this guy. Goes right there. And then we notice some symmetry. So we can go from 0 to r instead of negative r to r and just double our answer. Pull out that pi. And then the rest is identical to what I did. This is sort of what it would look like if we had different number of coins. So here we have a case where we only have 5 coins to approximate our ball. 1, 2, 3, 4, 5 balls. 5 coins. Right? So the face, zoom in. So here's where we have 5 different coins. So the first coin, this would be kind of like the purple circle of the first coin, and it would have a certain radius, which I was using capital R, and capital R is equal to a y value in the xy axis, which can be found as a function of lowercase r, the radius of the actual sphere, where in this case the actual sphere that they're illustrating is r equals to 1. So we can see that relationship between the two. Good. So if this was that purple circle kind of coming around like this, then that point there, and then this would come out here, and this would be a unit of 1. And then we'd have some x value, and this would be equal to y. Right? It still governs the case that x squared plus y squared equals to 1 squared. So y squared would be equal to 1 minus x squared. Good. Okay, so if we find the volume of the 5 coins, we add them together, that's a pretty good approximation. But if we do 10 discs, right, that's 10 coins, that's an even better approximation. If we do 20 of them, that's an even better approximation. And you can see where this is heading. If we do 100, 1,000, 10,000, a million, a billion, if we let that go out to infinity, eventually, at infinity, we'll get the exact volume of that sphere. Good. Questions, 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 questions?
So no matter what radius we have for any circle that we slice it, we can have it equal to that relationship, which is x, the one that you have right there, x squared plus y squared equals to the radius of the entire circle.
Right? So I think the answer is that they kind of vary a little bit depending on our equation. So this method does not work for everything. First of all, there's some things that just don't work that way, but it works for a lot of things. Things such that when you slice them in a certain direction, you end up with little shapes that can be like little coins. That won't always work, but in many, many cases it will, and that's the topic of this particular section in our book. So it'll work for the ones in this section, and we'll see some examples. But we're going to get some sort of a shape that we want to work with. We're going to slice it. When we slice it, we're going to get coins. We need to figure out how to get the radius of each coin as a function of the equation we're working with. And then we want to set up an integral that adds up all of those coins. When we're working with a sphere, if it has something to do with a sphere, then this will always be the relationship, that we're working with. But we might have something that looks something a little bit different, and so the value of r might be a little bit different. Also, we're going to explore something that's also called the washer method, which is little washers. It's kind of like a circle with a hole in the middle. So I want to refrain from saying that this is always going to be the case because they vary just a little bit, but they're all similar. They're all going to be tweaked a little bit. So we'll get to the homework and we'll do some kind of random ones from the homework, and hopefully I'll have a better answer for you at that point. Okay, I think that's pretty much what we want here. So this is just sort of general guidelines. The solids are all called solids of revolution because they are obtained by revolving a region about a line. In general, we calculate the volume of a solid revolution by using the basic defining formula that the volume is equal to a of x, some area as a function of x times dx. This will give you like little coins where a of x is the face of the coin and d of x is the thickness of the coin. Or if we cut it in the other direction, we'll have some function of y, area of the resulting coin as a function of a chosen value of y, times a little dy. Right? Again, we'll hopefully do an example that showcases that. And so we can find the cross-sectional areas a of x and a of y in one of two ways. So they will either make little coins, and when we have a little coin, we're going to have circles. We want to find the area of the circle, which is equal to pi radius squared, where that radius might get complicated. It might be as simple as saying, oh, it's the y squared, or it's the x squared, or it might be something else. Some other little equation might go in here that always describes the radius of the coins generated when we slice them. Good? Sort of, kind of, maybe, maybe. Okay. And then the other thing we're going to do in this section is think about cases where we have little washers. So maybe something like this. Think of this three-dimensional shape here that obviously has a huge hole in the center. It's like a bowl, right? If I slice them, I'm not going to get coins because every time I slice it, I'm also going to get something that has a hole in the center. Okay? So in order to deal with these, what we're going to do is find the outer one, deal with the outer one, pretend it was a solid coin, and that's what this is going to do. Pi outer radius squared. This gives me the area of the circle, and then we look at the hole in the center. That's going to be this empty, empty space here. Think of it as its own sort of empty coin, and it's going to have a radius of the inner radius, the distance from the center out to the edge where the things begin. So we're going to find the area of a coin that would fit there if there was no hole, minus the area of the empty space that does exist. Good. So that's what these two are. And so if I subtract those two, I'll get the area of the space that I actually want, and we multiply that times its dx, and then that'll help us get the volume of the individual washer. Is that okay? Kind of, maybe. And then once we have that, then we can, again, integrate. So if this is ranging from some value A to some value B, then we're integrating this whole thing here from A to B. And that'll give us the volume that we're interested in. Sort of, kind of, maybe. Okay, I think we should just dive right into some of these things because they get kind of messy. So let's just see what the homework has from this section. Okay, so here are the exercises from 6.2. So let's just grab one at least to get started. Let's get started with something really easy. Let's do number 4 to begin with. So we got y. It says find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. Sketch the region. The solid, and a typical disc or washer. Okay, so let's see if this thing finally works. Chapter 6, Section 2, number 4. We have y equals to e to the x. We have y equals to 0. And then we have x ranges from -1 to x goes to +1. And then it says rotate about the x-axis. Okay, so until that thing decides to work, we're left mercy of my terrible drawings. But we have x there, we have y there, and we have this equation here. So remember that e to the x power just looks like this. Good. And then we have x ranges from -1 to 1. So let me put it here from -1 to 1. And so we have y equals to 0. Y equals to 0 is the x-axis. So we are defining a little region that looks like this. From there to there, and from there to there. So we have a region that looks like that. And what I want to do is rotate it around the x-axis. So this is going to end up being something that looks kind of like a cone shape. This kind of comes this way like this, and then this guy goes like that, and this goes this way. That's as good as my drawings can get. Let me see if I can. Okay, so we had e to the x. It's one of my functions. So e to the power of x. I think it likes it wrapped in parentheses. Good. And then the other one was just the y equals to 0. Like that. Yes, and we went from -1 to +1 along the x-axis. Okay, so this is the guy. And now we want to rotate that, and when we rotate it, we'll end up with something that looks like this. It's got this kind of a coin shape to it, cone shape to it, right? And you can see right there, that's this thing is this thing. And you can see, depending on where I decide to slice it, perpendicular to the x-axis, I'm going to get different coins. And the coins are going to vary in terms of, whoa. Okay. Well, the coins are going to vary depending on where I slice it. Sometimes there'll be very, very little kind of coins way back there. And sometimes they're going to be really big coins like that one up there. Right? So the radius of each one of these coins is going to depend on where I decide to slice it. And it would make a lot of sense to slice my coins in this direction, perpendicular to the x-axis, right? Because if you look at the shape of this thing, if I start slicing it in this direction, then I'm not going to get coins out of it. Good. If I start slicing it in this direction as well, up and down, perpendicular to the y-axis, again, I'm not going to get coins. I get coins when I slice it this way. Now, one thing is, remember that this 3D generator here gives us, and might give you the impression that it's hollow in the center, but it's not. Okay, it's not hollow. I think if I increase this thing, it might look a little, well, not really. It still looks hollow, and it's not. It's not supposed to be hollow. Okay, so it's a solid piece like this. Anyway, well, hopefully this is enough to give you an idea. So here, let me see if I can make it look a little better. It looks like this. It's going to be a is that better? I don't know. It's like a megaphone or something. I don't know how to describe it. Anyway, something like that. I don't know if that looks better or not, but that's what the shape looks like. So this is going to be a 3D shape that kind of comes out this way like this. And now we're going to come in here and we're going to slice this up, right? So we're going to come in here and cut it perpendicular to the x-axis. And if I do that, then I'll end up with little coins. I'm going to exaggerate it just so that it looks better. But I'll end up with coins that look like that, where this is the width of my coin. And there will be a little radius to my coin. And the radius is going to be equal to the distance between the x-axis and this blue function. The blue function is going to determine that, right? So this guy, which was equal to y equals to e to the x, is going to end up being my radius value. Questions, questions, questions? Okay, so the area of each coin is going to be equal to pi r squared. Area of face of each coin is going to be equal to pi radius squared. And in our case, the radius is going to be equal to this equation. It's going to be pi y squared. But the y is actually equal to e to the x, and that gets squared, which is just going to be pi e to the 2x. Is that okay? So that's just the area of the coin, and now if I want to approximate, well, not approximate, the actual volume of each coin, volume of coin is just going to be equal to the surface area times its width, and its width is going to be the delta x. So we just take that guy. The volume now is going to be equal to pi e to the 2x times delta x. Good. So find, cut it up and come up with your own coin, the volume of a coin, and now we want to integrate, and we want to go as x ranges from there, x ranges from -1 to x goes to +1. So it'll be the integral of, so let's see, volume. Volume is going to be the integral as x goes from -1 to x goes to +1 of pi e to the 2x dx. In the previous one, we were able to come up with a shortcut and say, well, symmetry, we can just do half of it from 0 to 1, but we're not able to do that here. I hope that's clear, that based on the way the graph looks, there is no symmetry. So I'm not going to be able to say that this is twice something and simplify it. I'm just going to have to solve this guy. Okay? All right, now that's just a constant. You can pull that guy out, no problem. That'll be pi, and then x ranges from -1, x goes to +1 of e to the 2x dx. Now, if we think about just kind of guessing and checking for this, the derivative of e to the 2x is equal to e to the 2x. And then the chain rule would say times the derivative of the numerator, which would end up giving you an extra 2. And since we don't want that, we know that it must have a times 1/2 out here. Good. That gets evaluated as x ranges from -1 to +1. So this is pi over 2, parentheses, e to the 2 blank minus e to the 2 blank, like that, where first we plug in the 1, next we plug in the -1. Good. Okay, so we can simplify that just a little bit and say that this is equal to pi over 2 e to the 2nd minus e to the -2. Yeah, I don't know if that there's an easier way. We can probably just stop there. Or if we want to rewrite it as 1 over e squared, I don't know if that's necessarily better, but we could do this. E to the second over 1 minus 1 over e to the second. So e to the second is the common denominator. So we can rewrite this as pi over 2, and then e to the 4 minus 1 over e to the second. I don't know if that's necessarily better, but we can do that. But I think maybe that's probably good enough there. Any questions? No? Sort of, kind of, sort of? Okay, let's try another one then. Any suggestions? Anybody tried any of these already? Any hiccups? How about number 9? That rotates about the y-axis, so that seems fun. Okay, we have y squared equals to x, and x equals to 2y. Okay, so it's going to be a linear equation with a slope of 1/2. And this is going to be kind of like a parabola tilted on its side, right? Or square root of x plus or minus the square root of x. You can also think of it that way. And then those two get rotated about the y-axis. So this is chapter 6, section 2, and this is number 9. And we have y squared equals to x, and we have x equals to 2y, and we want to rotate about the y-axis. Okay, so again, we're at the mercy of my drawings. This guy is going to be the same thing as plus or minus root x, so it'll look like this, and then it'll also kind of come this way. And then this guy is going to be a linear equation with slope equal to positive 1/2, right? I can always just move this around and say it's 1/2 x equals to y. Just like over here, I could say that y equals to plus or minus root x. Okay, so then there'll be a line here, and I believe this line is going to end up looking something like this. Where they intersect here and they intersect there. So obviously they intersect at 0. So 0 squared equals 0. 0 squared equals 0. Yep. So that point right there is the point 0, comma 0. And this one's probably 1, right? 1 squared equals 1, true. And, oh no, 1 equals 2, that's not going to be true. But what about, what's the other one that's true here? That's going to be easy. 1 and 2. Two and 4. So x equals to 2y, and y squared equals to x, I'm looking for the point right here where they equal each other. I don't know, let's call it a and b. I'm looking for a and b so that they equal each other. At that point, at that ordered pair a and b, both of these two statements must be true. So it must be true that a is equal to twice b, and it's also going to be true that b squared equals to a. Okay, so from that, I can set them equal to each other. They both equal to a. So 2b must be equal to b squared. So I could so I can do 2b minus b squared equals 0. So b equals to 2 minus b equals to 0. So one option is b equals to 0, which we already have. And the other option is going to be 2 minus b equals to 0, which means that b equals to 2 is the other option. And if b equals to 2, then from b squared must be a, it must mean that 2 squared equals to a, a, so 4 equals a. A, so 4 equals A. Okay, so we have our choices here, and I should have noticed it, 4, comma 2. But then we can just double check here, make sure it's true. If the x value is a 4 times a half, that gives you 2. Yep. Or if you put a 4 there, it's perfect. Yep, that works too. Okay, so we have those 2 points there. And we can also graph them on Desmos. Desmos should hopefully work. Desmos. Y equals to x to the second power. Oh, sorry, the other way around. It was y to the second power equals x. It's like a parabola on its side. And then we also had y equals to y, something like that. And then that's where they crossed, so they look like this. Okay, so we're going to be looking at this little region right in here. And we want to rotate it about the y-axis. So we want to take this little curve, this little weird region here, and we want to rotate it this way about the y-axis. So we have this little region here in, let's put it in red. And what we want to do with this little region is rotate it about the y-axis. Right, so here's our y-axis, here's our x-axis. So if we rotate it, kind of think of putting it on, something that rotates really fast, spins really fast, then we're going to end up with something that kind of comes across this way, like that, and it comes down to a dot, to a point, but it maintains this sort of thickness all the way throughout. So over here on the outside, it's going to be like a flat cone. From the outside, it's going to look like a flat cone with a smooth wall around on the outside. But on the inside, we're going to have this curvature that kind of comes this way and goes this way. Wow, that was really ugly. That, I guess, as it rotates. Sort of, kind of, maybe. So it's gonna come out to a specific point. So it's gonna have a sharp edge at the edges here, and then it's gonna come down to a sharp point. So the general sort of the shadow image of it is gonna look like a very, very pointy point. I mean, a very pointy cone-looking thing. Good. except that instead of being solid, it's going to have um, not quite a hole since it goes to a dot, but it's going to have kind of like a little cave thing in here. Right? It's going to kind of come down this way and disappear into the center of it. Right? So it's going to have like a little thickness to it. It's going to be hollow in the center of it. Good. Sort of, kind of, maybe. I wish I was a better drawer for you, but you know, this thing is hollow. It's got a little hole thing. It kind of comes this way. Right? And then it comes up to this very sharp edge around the edges here. You guys sort of see it, I hope. Best I can do. Okay, so now let's use technology to get a better image of that. So the functions we're working with were square root of x to the power of 0.5 gives me positive root x, and the other equation was 0.5x so that's the other one. Let me zoom out a little bit more. Okay, and then we saw from our work that they go from there to there. They cross at the point 4, 2. So I need x to go from 0 up through 4. Okay, so now we have that nice shape right there. From this point, which is the point 4, 2, this point, which is the point 0, 0, and we're going to rotate it about the y-axis. Right, so real quick point here. This was already set up from the previous one to rotate about the x-axis. So notice how this is the shape if we rotate it about the x-axis. If I take this guy and start rotating it, it's got a nice smooth curvature, right? The root x dominates the outside wall, so it looks like a vase, like a bowl, right? And then it's maybe a little hard to see from here, but the inside of the bowl, come on, what was that perfect spot? It's kind of hard to see, but there we go. See the walls of the inside of this bowl, the walls are dominated by this, so it comes down to a very sharp corner at the edge. So it's like the hollowed out area is like a perfect cone shape. Okay, but this problem was not, there we go, that's what I was trying to get. So right there, see it's a straight line, and so it'll carve out this hole inside there that's like a perfect cone. However, this problem wanted us to rotate about the y-axis. So now we might be in trouble because I don't know how to do that. Disk shelves. Let's see if I do that. Oh, okay. I think that did it. It rotated about the line x equals to 0, and we still have this function, that function. Okay, vertical shelves, and that's what we have. Okay, good. So from the outside, we have a nice perfect cone. So if we rotate it around this way, the outside will be this nice perfect shaped cone. But the inside, and it's a little hard to tell, but the inside has got this nice curvature that curves into it. Looks better if I zoom out a little bit more. So it's a little hard to tell with this. Would it look better or worse if I put more ends? I don't think it looks any better. Anyway, so it's got a little bit of a thickness. It comes out to a very, very thin edge at the edge here, but then it gets a little thicker, 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 right? It follows this, right? If I put it just this way, we can see that if I cut it with a knife here, the cross section would be this little tip here, would be this point right there, and it would come to get a little thicker, and then it like comes down to be just that guy right there. Okay, I think that's as good as it's going to get with this guy. And then so as I start slicing, you see that I end up getting these washers that come out of this thing. Let me make this a little bit. No. Maybe if I change it to Okay, so I cheated a little bit the system because I wanted to stick with the discs and wouldn't let me rotate about the y-axis. So I flipped these around. Instead of making it square root of x, I changed it into x squared. So we have that same sort of a curvature kind of function. And then instead of having 1/2 x, I changed this to 2x. So we end up with this straight line there. It still goes through this point and that point, which is going to be the point 2, 4. And now if we rotate it about the x-axis, we're going to get the exact same shape as we did before, except that instead of having it rotate about the y-axis and having our shape here, it's going to rotate about the x-axis and have the exact same shape kind of tilted on its side. Right? So once again, this is what the intention was, to rotate it this way, but then if I just play around with it and rotate it this way, then I get the same picture. So this is just for the purposes of my graph here so that I can get a better image of it. So I think this looks a little bit better. So now, as I go through my dx, we can see that we end up getting washers. This is the washer method. You see how they're almost like coins, except there's a hole in the center of it? And now for any coin that I choose to slice through, there's going to be two radiuses that we worry about. The radius, one radius is going to be from the center all the way out to the edge of the coin, whereas the other one is going to be from the center out to the edge of where the yellow begins, sort of this empty coin in the middle. Got that? Good. So now if I was looking at it this way, there would be two radiuses from there all the way out to the outer edge, and as you can see, that's governed by the straight one, the straight line. And then the other radius would be the one that goes from there out to the inside, which is the curvature one, right? So there's going to be two different radiuses that we care about. So let me find a good picture for this thing, maybe from let's do a couple, I guess. Let's do this one. And then let's do a nicer one. Yeah. Right, and of course, as we choose the different places where we cut it, the actual size of the washer is going to vary. Good. So sometimes it's going to be a very thick yellow part, and sometimes it's going to be a very, very, very thin yellow part. Right. So there are different types of washers that kind of come through. The center to the inner edge, remember that's the radius of, that radius is measured from the center all the way out to the inner edge, which is governed by the curvature, the root x in our case. And then the other radius is going to go from here to the outer edge of our shape, which is going to be governed by the straight line. Good. So let's take pictures. Pictures. And let's do one more that's more of like that. Okay, so let me get out of here. So I have that guy, that guy, I have that guy. Okay, so as we slice through it in different locations, notice that for us, like I said, I had to mess around with the technology a little bit just to get the perfect image. But for us, back to us, this is the y-axis, and this is the x-axis, like this, right? We had that this straight line, the straight line was y equals to 1/2 x. And we have that curvature one, the curvy one, that curvy one, is y equals to the square root of x. Good. So we're going to have, to figure out the area of the yellow. To figure out the area of the yellow, we're going to find the, the volume of the coin, which is the washer, the volume of the washer in yellow here. And what we're going to do is we're going to find the volume pretending that it's one big solid coin. So if we do that, we need to care about the radius from there all the way out to the outer edge, like that radius. And that radius, capital R, that radius is going to be the same as the radius from here all the way out to here, right? Which is governed by the straight line. R sub, I don't know, the right one, the right radius, I don't know, the large radius, the larger value. Good. And then we want to think about the smaller radius, the one that goes out from the center of where I cut my coin all the way out to that inner edge there. And that's the other radius. I'm going to call it, for this purpose here, let's call it r sub large and r sub smaller, the smaller radius. Good. So that'll be the radius that goes from here out to right there, kind of governed by the curvature one. And that'll be this radius from there to there, which we're calling r sub small, the smaller radius, which is going to be governed by the curvature one, right? It's going to come down to here, and it'll be some value there, which is the r sub the smaller one, right? Determined by that curvature. And all of that will be for a specific value of y, right? So remember, we're slicing it perpendicular to the y-axis. So when we choose a value of y, we're going to get two different outputs for x. There will be an x sub left and an x sub right. There's all kinds of ways to name it. And so we're going to find the volume of the outside, the volume of the solid coin that goes out to the outside using this as our radius. And then we're going to find the volume of that empty space, the empty coin. Subtract those two, and that'll give you the volume of your washer. Good. Questions, 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 questions? Now, in all of these, I don't know, does it make sense? So from the center of this washer, let's say that that's the center, then out to the edge, right there, that's what I'm calling the larger radius, r sub large. And then from there out to the start of the inside, sort of that empty space, that's what I'm calling r sub small. Good, 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 good. And then that's just based on where I slice this guy, that you generate that. Okay, so we're gonna cut coins through this thing, and the best way to cut coins is not gonna be this way, right? If I cut coins this way, if I get my knife and start cutting this way, I'm going to get weird shapes as I slice through this thing. So instead of slicing it this way, I want to turn my knife around and cut it this way, perpendicular to the y-axis. If I cut it perpendicular to the y-axis, then I am going to get the outside is going to be it's going to be a washer, right? Where it's going to end up being an outside circle with a little empty circle in the center. Good. So let's see, what kind of color can I do? Let's do red's going to be the same thing. Let's do it this color. Okay, so if I slice it this way, it's going to go from there to there, and then across this way. And it's going to have some sort of thickness to it. Okay, so here is the beginning of what I get. Except that it's not just a solid coin, it's going to have a little hole in the center that looks like this. I don't like that. Let's see. It's going to have a little hole in the center. No matter how I draw it, it looks terrible. Whatever. Close enough. So it's going to have a washer looking thing. It's going to have a thickness, which is going to be a delta y, a thickness to this, almost like a coin with a hole in the center, a washer. Coin with a hole in the center, and there's going to be two radiuses that we're going to care about. 1 is going to be the radius from there all the way out to the outside, right? The radius of the big thing is going to be the distance between the center and the equation, this equation right here, which is y equals to 1/2 x. Right? So that will determine the outside radius. And then there's going to be this inside radius, and the inside radius is going to be the distance between the y and the blue one, which is just equal to y equals to the root of x. Good. Notice that we don't really care what happens down here now. Based on what I'm rotating, I'm not going down below the x-axis, so I can just ignore that minus root x part of it and just say it's y equals to the square root of x. Good. Good. Okay, so now I can also write it in terms of y squared equals to x. Or over here, I can write it in terms of 2y equals to x. So both of these are representing the relationship between the values that are on this green line here. This green line here. Good. And both of these equations are describing the relationship between all the ordered pairs that are on this curvature there. Good. Okay, what I care about is which one do I want to use, this equation or that equation, and that depends on my variable of integration. I'm going to use a delta y. I'm going to be slicing it in this direction. So for each individual coin, I'm going to choose a y value, and that y value needs to give me an output of an x so that it can be the radius along, for the outside one. Right? So if I'm looking at the green function, I'm going to be choosing a y value, right, for a particular choice of y. Then I can plug it into this equation, double it, and that gives me the value of x, which is the radius for the outside one. Good. Okay, so let me write down what the answer is, and hopefully it'll all kind of come together. Okay, so I want to do washers, and so the volume is going to be equal to the integral as y ranges from 0 to y goes all the way up to this point right there. The y is a 2. Okay? Y equals to 2. That's because I figured out where they crossed. I did this whole thing with a and b. And now once I figured out where they crossed, that means that this a was actually equal to 2, and this b is actually equal to 4. So now I'm integrating from y goes from 0 all the way out to 4. Oops, b was 4. Wait, did I skip these? It's the other way around, isn't it? A was 4, A was 4, and B is 2. There. So y is going to be integrated from y goes to 0 to y goes to 2. Good. Okay, with the washer method, I want the pi. Oops, I don't want that. I want pi of outside radius squared dy, minus pi, and then inside radius squared dy So I want it as a function of y. So the outside radius we said was this green one. So this is what the equation I want to use. 2y, right? 2y equals x. So when you choose a y, you double it, and then that'll give me my x value. And then that gets squared. So that's what goes in there for the outside radius. And the inside radius is going to be this blue one. Again, I want to plug in a particular value of y, and then that should lead to the x value. So once you choose a y, you square it, and that's what gives you the x. So this should be the y squared value that goes there. Good. All right, so let me simplify that. The volume is going to be the integral as y ranges from 0 up to 2 of pi times 2y squared minus pi times y squared squared, all dy, which then is equal to the integral as y ranges from 0 to 2 of pi times 4 times y squared minus pi times y to the 4th dy. Okay, so this is a fairly simple integral to solve. So I'll put it's equal to, so the first one is just going to be equal to 4 pi, that's just a constant, times, and then this is going to be equal to 1/3 y to the 3rd power. That should give us that antiderivative for that guy, minus pi, and then the antiderivative for that one would be equal to 1/5 y to the 5th, evaluated as y ranges from 0 all the way up to 2. Good. So that'll be equal to 4 pi over 3. This is a pi. 4 pi over 3, and then something cubed, minus pi over 5th times something to the 5th power, minus the same thing, 4 pi to the 3rd, something to the 3rd, minus pi over 5, and then that's something to the 5th power. And the thing we plug into here, it's going to be a 2 there, a 2 there, and then a 0 there, and a 0 there. Luckily, that makes this whole thing super easy. That's a 0 there, that's going to be a 0 there. So that whole term disappears. So I only end up with an 8 and a 32. So that'll be equal to 8 times 4, that's going to be 32 pi over 3, right, because this is an 8. 8 times 4, 32 pi over 3, minus 2 to the 5th is 32. That's 32 pi over 5. Common denominator is going to be equal to 15. Want to get a common denominator going. So let's multiply this one by 5. 5 times 32 over 5. This one times 3. That's ugly. That's going to be 150, 160, 160 pi minus 96, 96 pi over 15, which gets me to 64 pi over 15. And that should be my answer. Any questions? Questions, 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 questions? No? No, no, no? Alright, I think this is a good place to stop for now and let you guys practice some of these. And I'm going to go back to try and figure out how to fix the graphing thing, because it would be really nice to have it in this section, because my graphing skills suck and these graphs are just going to get more and more complicated and it's hard to visualize them without a good graph. Okay? So,
question.
Yeah.
So are we allowed to use that website that you're using? Because I can see that it's going to be hard to, as you said, hard to visualize.
I mean, you're allowed to use it to help you understand the graph and what you're supposed to do, but ultimately when, you know, the test comes along, I need to see something that looks like this as far as work goes, so you can kind of sketch something and, you know, kind of hopefully get a good sense of what it looks like and all that, and show your work and figure out the result. The only thing I don't want, the only reason I'm a little hesitant to say, yeah, you can use it, is because I don't want someone to just kind of mysteriously give me the answer and they got it because they went to some website and you just type it in there and it just tells you the volume and you're done, right? So you do need to show all your work, but you're welcome to use any technologies out there to assist you in understanding and visualizing what it looks like. I'm okay with that. So feel free to use it, graph it, get a good idea, a good sense of what you're supposed to be doing, what it looks like, and then come back and try and do it, you know, showing your work, by showing your work and figuring out the actual setup of the integral that you need to solve.
All right. Thank you, Professor.
Okay. All right. Okay. So this would be a good place to stop. Go ahead and try out stuff from chapter 2, section 2. Okay. All right. Have a good rest of your day then.
Take care, Professor. Thank you.
Have a good day.